Okay, let's start. We want to talk about fractions. Now, I'm not going to talk about what fractions mean. I assume you know that. But, okay, a typical answer I get for what's 2/5 plus 1/2, say, is, well, add the 2 and the 1, add the 5 and the 2. Okay, they're confusing rules if you do that, but since most of what you've been taught in mathematics and most of what the SOL tests you on just involves short-term memorizing rules that you later forget, you don't have it. And as I just said, this course is a transition between that kind of learning and the kind of learning that's actually beneficial. And of course, that kind of learning, I'm all blurry. Okay, there we are. If I was blurry, this was blurry. Okay. Fortunately, I happen to look back at that thing. It's often depressing to do that, but sometimes I do. Okay. Now, so again, we're making a transition between the kind of learning that you've been able to do that did give you some foundation so you can learn how to think a little better, okay? And the kind of learning you have to do to be able to use mathematics a little bit, which keeps doors open for you and all that stuff. Okay, so if we try to add these, no way, that's the wrong rule. Why? How can we tell that's wrong? Well, because this gives you, and I think I said 3/10, it's 3/7, right? Two plus 1 over 5 plus 2 is 3/7. Which is less than 1/2. And since 1/2 is one of the numbers that's being added, and since these are both positive numbers, we sure aren't going to get something less than that, right? Because we know when you add two positive numbers, you get a number that's bigger than either of them. Okay? And that's a little deeper thinking than just trying to remember the rule. Okay? And it also gives you a way to check out the rule, because it's real easy to write down something like that without thinking, right? And of course, that's why we check our solutions. Okay? That's a little harder to check that solution. So what you would want to do is think about, well, you know, if I get the right numbers here, I can easily get a case that contradicts the idea that you can add the numerators and add denominators. Okay? I won't go too far with that because that's a skill that develops more or less gradually. What you do is okay, well, certainly I can say this. 2/5 is the same as 2/5 times 2/2, isn't it? Why is that?
Because 2/2 is 1.
Yeah, and 1 times 2/5 is just 2/5. And similarly here, 5/5 is just 1, so we're not changing the value of this number or this number by doing this. Okay, well that equals 4/10 plus 5/10, right? And that means 4/10 plus 5/10, okay? Well, how many tenths do you have if you add 4 of them to 5 of them?
9 tenths.
That's common sense, okay? Now we get more rigorous about it, but we're not trying to teach a mathematical analysis class here, okay? And I'm not talking about like a high school mathematical analysis class, I'm talking about a higher level analysis class. So we can only go so far, but the common sense of this is, if I know how many tenths this has and how many tenths this has, then I can just add how many tenths there are and this one, and get how many tenths there have to be, right? Okay? So the rule is, if you got the same denominator, then this number will tell you how many of that you have, and this number will tell you how many of that you have. And you have. Then you can add the numerators, but you don't add the denominators. You're adding how many tenths to how many tenths, you're going to get how many tenths. That's kind of a common sense application that makes it clear why you're doing this and what you're doing. It's not just a rule that says you find a common denominator, okay, which you kind of, yeah, I'm sure you remember. I'm sure you know how to do that, if, yeah, once you're reminded. It goes a little deeper than that into what it really means. Okay, and you want to think about what it really means, but of course, you also want to be sure you remember what the rule is. Okay? And you remember the rule better if you remember what it means. It's a direct connection. Okay? So, that's pretty straightforward, right? So let's add 5/8 plus 7/12. Okay? Now I'm going to say that's equal to something. And what am I going to do to 5/8? You guys are pointing at each other.
Take the floor, Jordan.
Well, what did I do to 2/5 here, and why did I do it?
Multiply it by the numerator.
Okay, well, I multiplied by some number over some number, right?
Equal 1, yes, yes, sir.
Yeah, do what?
No, nothing, just, I was probably wrong anyway.
That's probably right. Yeah, remember, I can't hear very well. Okay? Well, what I'm trying to get is both of these denominators need to end up the same, right? And to get them to end up the same, I'm going to have to multiply this by some number and this by some other number to make them the same, right? Now, one thing that always works, it's not the most efficient thing, and you want to do it efficiently, but one thing that always works is if I multiply the two denominators, well, I can always get that. That's what I did here. I took this denominator and multiplied it by the denominator here, right? And I took this denominator and multiplied by this denominator. It obviously gave me the same number. Okay? Now, of course, I can't just multiply the denominators. I can only multiply by 1. So if I want to multiply 5 by 2 down here, then I better multiply this fraction by 2 divided by 2, because that's 1, as you saw, right? And then I'm going to have 2 times 5 here. These are going to end up the same. And so I multiply by 5 over 5. Because whatever I multiply the denominator by, I've got to multiply the numerator by. We get to 1, as you saw. So I could do this very easily. I could say, well, okay, let's do 5 over 8 times something plus 7 over 12 times some number over itself, so that the denominators will end up the same, right? Okay, well, it certainly works if I use this denominator over here and this denominator over here, because my two denominators are going to end up the same. It's obvious. Okay? So this is 60 over 96, and this is 56 over 96. And that gives us 116 over 96. And watch my arithmetic, because I can make mistakes. Okay? I'm pretty good with arithmetic, but also I don't have as much working memory as I once did. Okay, so I can do ignorant things sometimes. So I'll always take my arithmetic with a grain of salt, but I think it's right this time. Okay? Now, what about 116 over 96? Is there something we need to do with that?
It would turn into one, something, right?
Again?
Would it turn into one and then another fraction?
We could write it as a mixed number, but in this course, we're pretty much not going to do that unless we need to graph it. Okay? Because to see that that's 1 and 20 over 96 tells you where to locate the point on a graph, right? It's between 1 and 2, closer to 1 than 2, and all that stuff, okay? So that's an important thing to be able to do, so you got to know how to do that. But we're not going to talk about that right now, because I assume you can do it. And if it turns out you can't, you know, we'll address it. Okay, but what you can observe is these are both even numbers, right? Which means what? You divide them both by 2. Okay? Well, you know that if you got fractions, you want to get them in lowest terms. You got a denominator of 96 here. What's 2096 look like anywhere? What's 160? Those are kind of big numbers, and sometimes you can't avoid that. But we can reduce this by dividing both of these by 2, and we get 58 over 48, right? And of course then, these are still both even numbers, right? We can divide these by 2 and we get 29 over 24, okay? And now 29 is a prime number. There's no number, no integer that divides it without a remainder. So there's nothing we can divide this by to simplify, okay? So we get 29 over 24. Now let's revisit this problem. 5/8 plus 7/12, okay? Is there a smaller number that's a multiple of both 8 and 12? What is it?
2.
Huh?
2.
No, that's not a multiple, that's a divisor.
Oh,
4.
No, it's not a multiple. A multiple, like 96 is a multiple of both numbers. There's something you can multiply 8 by to get 96, and there's something you can multiply 12 by to get 96.
24.
24, right? That'd be your least common denominator. It is your least common denominator because you could actually think, okay, what are multiples of 12?
24.
24 is your first multiple of 12, and bingo, it's a multiple of 8, right? So you found one. Or if you wanted to start with 8, 16 is a multiple of 8, but it's not a multiple of 12, right? 24 is a multiple of 8, and it is a multiple of 12. Okay, so if we want to get denominators of 24, well, what do we have to multiply 8 by to get 24?
3.
3. So we multiply that by 3 over 3. And what are we going to do with 7/12?
Times 2.
Multiply by 2 over 2. So 5/8 plus 7/12 equals this, which equals 15 over 24 plus 14 over 24, right? Okay. And now we're adding 24ths. We got 15 of them, we got 14 of them, that gives us 29 of them. Make sense? Okay. And of course that agrees with what we have here, because however you do this, if you reduce your fraction to lowest terms, you're going to end up with the same thing. This was a little more work, a little more pain, a little more opportunity to screw up. Okay? So this is a little more reliable, and it also makes reducing it to lowest terms a little easier. Although it's pretty easy to reduce this. Okay? It's not always. Now you won't always get something that's in lowest terms. Okay? If this had been 11 over 12, let's say you would have gotten 22, no, I still wouldn't have done it. 9 over 12, of course, isn't in lowest terms, but if you had 9 over 12, no, that wouldn't do it either. I'm not even going to try to think it through. Okay, I'd write an equation to do it. I can think about it a little more. Find a number maybe you could have used here or here that would have given you something that has to be reduced. It's very easy when you're adding these two numbers to get something that has a common factor with this one. And I can think of numbers, but they all reduce. So maybe there's a theorem there I haven't thought about in a long time. You don't need to worry about it. Okay. You want to worry about me, go ahead. Okay, now, you get the idea. Okay? So let's say now that I want to add A plus B to C over D. A over B added to C over D. Okay? What's my common denominator going to have to be? Well, one thing we saw here is you get a common denominator if you just multiply your two denominators, right? Okay? So B times D has to be a common denominator that you can get, okay? Common denominator could be B times D. Okay? In other words, we're just going to do with these letters what we did with the numbers, except we don't know what the letters are, so we don't ever have to worry about what the least common denominator is. Just the simple product of the two denominators is going to be our common denominator. Okay? Unless we know more about the numbers B and D, that's all we can do. So we have A over B, and we have C over D. What are we going to multiply by A over B?
D divided by B.
D over D, because that's going to give us B times D, right? So we got to have, in order to get a common denominator, you can kind of look at it like this. You got to multiply this denominator by D, and now you got your common denominator, right? And over here, you're going to have to multiply by something over B so that you have the same denominator. You get this common denominator. And of course, when you multiply, you want to multiply by something that's equal to 1 so you don't change the value of your fraction. You just change the way it's expressed. Okay? That makes sense? I could write this as DB because that's the order, but multiplication, order of multiplication doesn't matter. So write it in alphabetical order, which is kind of the standard. You know, not absolutely necessary. Well, now I have the same denominator, and for the same reason, I can then add the numerators over here because I'm adding tenths to tenths, right? Or adding 24ths to 24ths. I'm adding whatever B-diths, okay? But we don't want to get to that terminology, okay. By the same rule, it has to apply for the same reasons it did before. That's what I get. Okay? Now everything here is algebra 1 or less. So I expect you to be able to review that. And when I post your homework, I'm going to go back to an intermediate algebra text, the first chapter on fractions, and then to a later chapter on something else called rational functions, because that's what we're building toward, and that's something that is a big stumbling block when we get about 2/3 of the way through the course, halfway to 2/3 of the way, okay? Is how you add fractions with symbols, especially if the symbols look like, well, you'll see in a minute, okay? So, let's try this. Going to add these. And those are just fractions. They're actually what we'd call rational expressions. But we'll worry about that terminology later. We just do what we do with fractions. What's the common denominator going to be?
X minus 2 and x plus 5.
X minus 2 multiplied by x plus 5. So the common denominator, now we got to be careful how we write this. Okay? Got to have the parentheses, otherwise all we're multiplying is negative 2 by x, right? We're not multiplying this whole thing by this whole thing. We'll talk about the distributive law next to make sure we understand what this multiplication means, because that's another big stumbling block throughout this course, throughout the pre-calculus course. Okay, so we have this. Okay, well, then as before, we need to multiply by some fraction, right? Or some rational expression, if we want to use the proper terminology for what these are. Okay? But the rules are exactly the same. What do I have to multiply x minus 2 by to get this? I've got x minus 2, right? I want to get x minus 2 times x plus 5. So what did I better multiply x minus 2 by? So obvious you didn't want to say it, right?
Oh, yeah.
You're sitting there thinking, how am I going to answer that question? Bonehead, we know what it is. Why don't you just tell us? Okay? You can call me a bonehead, it's all right. That was one of my nicknames in high school. Okay. Fat Boy called me Bonehead. Fat Boy's the best athlete around. He's one of them, yeah. One of my 2 or 3 closest friends. We were always playing football after school. And where we grew up, football was the only game. The only reason we played any other game was because it was in season and it was politically correct to play basketball or baseball. Soccer wasn't a game. We didn't understand the rules. We were just too dumb. It's a great game. We didn't regard it as one. And Fat Boy was fond of calling me Bonehead. And since I was, and Fat Boy is one of the smarter guys around too, but I was supposed to be one of the, one of the smartest guys around. So other people thought it was totally funny that I was called Bonehead. Also, it was sometimes appropriate, to be thick-headed. Okay. So anyhow, if you want to call me Bonehead, it's a compliment. Anyhow, okay, Bonehead. Now, why did you multiply it by x plus 5? Well, because, duh. You see it. Okay, so we have x plus 5 here, right? And over here, what are we going to have to multiply x plus 5 by to get this? Yeah, see, you're not afraid to answer now. You know I'm a bonehead, you can say anything. Okay, get this, right? Okay, well then, what's that equal to? Well, that's x plus 4 times x plus 5 plus x minus 1 times x minus 2. All divided by x minus 2 times x plus 5. Okay? Incidentally, Fat Boy lived in a house with 40-yard lots. It's a 40-yard lot, 40-yard lot next to that. Paced it off. We knew where the boundaries were. He could stand at this boundary. I'd take off running. 5 minutes later, I'd be halfway across that second lot, and he'd throw the ball, and I'd catch it right at the 40-yard there. He could throw a ball 80 yards. I thought I had a weak arm. I could only throw it. Yeah, at that time I was throwing it in the upper 40s. Ended up throwing about 55. Never thought I had a strong arm. That's not a particularly strong arm, but that's fairly typical of the high school guys that go to these things on television. They're throwing in the low to mid 50s, some of them further. Now, pro quarterbacks most of them can throw at 80. Difference between him and me is he could hit what he was aiming at. You know, everybody in the stands was in danger when I'd throw the ball. Okay, so I was not a good quarterback. Takes more than a reasonably strong arm. That's relevant to something. I was going to make a connection. I'll figure it out later. Okay, so there we go, right? It's relative to what's relative. You know, it turns out I had a fairly strong arm. Never thought I did because of Fat Boy. So, you know, you got to be careful about who you're trying to compare yourself with, right? You know, there's always somebody against whom the comparison will be depressing. And if you have a tendency to compare yourself against the best, and I can throw it further than anybody else around, but you know, not that much further. Okay. They're analogies. Okay, now let's go here. Okay, we see how this comes about, right? Now you understand how I got from here to here? Because, you know, I got to put the parentheses around these things now to multiply them, because I'm not just multiplying the 4 by the x. I'm multiplying the whole x plus 4 by the whole x plus 5, and similar across all of these expressions. Okay, so we have this. Okay, now, here's where things get a little bit complicated. And I alluded to this in class last week, but let's be careful about how we multiply these things. How do you multiply x plus 4 by x plus 5? And there's one word that I kind of forbid from my class. It's that F word. Starts with F, ends with L. A couple of vowels in between. Okay? That's not fool. Oh, that's not a good nickname. But it's how you learn to multiply binomials. Okay? I forbid that word. Okay? It's socially inappropriate to use that word in my class. You use the distributive law to multiply things, because that F word thing only applies to binomials, whereas the distributive law applies to anything. Now that F word thing is very handy when you're trying to factor trinomials. Okay? But not when you're multiplying. Okay? Okay, so, well, x plus 4 times x plus 5 equals x multiplied by x plus 5 plus 4 multiplied by x plus 5. What rule did I use? Or what law?
Distributive.
Distributive law of multiplication over addition. We talked about that in class. Okay? Multiplication distributes over addition. Remember I talked about how raising to an exponent doesn't distribute over addition, although it would distribute over multiplication. Okay? So there are other distributive laws, but you don't want to let the fact that there's a distributive law of multiplication over addition cause you to use it when it isn't appropriate. So like x plus 4 squared is not x squared plus 4 squared, because you don't distribute exponentiation over addition. You use the distributive law. We'll say more about that. You hear me keep reinforcing that because people continue to make that mistake throughout the course. So you have this. Well, what's x times x plus 5? How are you going to simplify that?
You just multiply the x by the x and the x by the 5.
What rule did you use there?
That's it.
That's a distributive law again.
Oh, that's true. Okay.
Yeah. Okay. So we're using the distributive law twice. We have to use it to break it down to this. Then we use the distributive law on this because we're distributing a multiplication x times this over the addition. And you know what it is because you know it from habit. But again, we're trying to get away from habit and base things on rules, because habit can lead you to try to add fractions by adding the numerator and adding the denominator, right? There's a related habit. It kind of feels all right, but it doesn't work. Okay? So we're trying to put the mathematics in a little firmer ground. Okay, so anyhow, by the distributive law, this is what we get here, and here we get 4x plus 20, right? And then that becomes x squared plus 9x plus 20. Okay? Now, I see people do what I did, but I understood why I was doing it. You know, I just kind of draw a little arc from here to here, and a little arc from here to here, and one from here to here, and one from here to here. I see that a lot. Okay? That's okay if you're able to, when I ask you, use the distributive law one step at a time. Okay? And I also see kind of a grid thing where you put the x and the 4 here and the x and the 5 here and then fill in the squares. I didn't used to see that. That's got to be something new in some of the high school textbooks, or maybe even in the materials we use for our MTEs. I've taught that course just one time and haven't seen it, but I might not have been teaching that particular MTE in that section. So I don't mind seeing that if you can base it on the distributive law. So I might well have questions in the test. How does the distributive law allow you to do this, or how does it allow you to make that table? Okay? What's the relationship? The distributive law is a distributive law. And we need to know, in order to base what we do on actual rules, we need to do that rather than draw arcs and draw tables and use superstitions of various forms. Okay? Okay, so we do this.